So apologies to the recording because it'll probably go a little bit fast, but then we'll try and spend some time talking about how to solve questions. This is one I don't believe we actually solved, right? Oh, we did do this one? Oh. Did we? So plunging lithium, we did talk about all the bonding of metals. Talked about our band gaps. These materials. So for y'all, I did say we'd come back to this, so we should come back to this. So which of the materials could also act as semiconductors? So what are we looking for if we're trying to find semiconductors? We're trying to find something that mimics silicon. That's our biggest kind of plot within this. And I believe what I'd mentioned for y'all, and I could be wrong, is that one of the other kind of common categories for our semiconductors would be our 3-5 materials. Does that make sense? Okay, so if we were looking at our 3-5 materials, and I don't think I drew this out for y'all, so we'll draw it out real quickly. What we're talking about is our S and P orbitals. So for our valence shell. So we've got our S orbitals as just that single orbital, and then our P orbitals, we've got 3 sets of those, right? So if we're looking at a 3-5 material, what does that mean? 3 is referencing our valence electrons. So if this is our 3 material, so we'd have 1, 2, and 3 valence electrons. Make sense? What happens if we look at our 5? 1, 2, 3, 4, 5. And the big deal that we're seeing is those 4 unfilled electrons, or those 4 unpaired electrons. That becomes our big deal when determining our semiconductors. So if we go through and look at these composite materials, what we want to be looking for are things that kind of match that pattern for silicon. Right, so if it's 3-5, anything in the group 3 column, partnered with anything in the group 5 column, matches as a 3-5 semiconductor. So what do we have? Say again? Say again, but try and change it. That's an I.
Oh. I and B.
That would be indium phosphide. So indium is in that group 3, phosphorus is in that group 5, and we're looking at an indium phosphide could act as a semiconductor. Do we have any other semiconductors that could act as 3-5? Okay. GAAS. You guys have never been asked to memorize your elements, huh?
Gallium and
Oh, okay. I feel a little bit better about that.
Yeah.
Okay, just checking. Okay, so that's gallium and arsenic. Right, those are sitting on our 3-5. Do we have any other 3-5s? No? Okay, what are the other ones? Cadmium's a little bit weird, so let's skip cadmium for the moment. How about GaSe? Gallium selenide. What's that?
3-6.
Gallium selenide would be a 3-6, so that doesn't fit our 3-5 pattern. Okay. That said, we drop back to our cadmium sulfide. What's that one? And that one might become trickier. Hopefully the sulfide stands out. What's the sulfide? That one's a 6. What's the cadmium? All right, and this is where things are going to become a little bit tricky because we would think to bring in our d orbitals. When we're talking about valence electrons, we're not bringing in d orbitals. So no d orbitals. Ignore those. How many valence electrons does cadmium have? No d orbitals. 2. Okay? For the, where did it go? The 5s. Okay? Do we have a little bit of a hint that could help us with that? How did we know we were in the 3 or 5 categories? So we could just go how far they were across. What else did we have as a hint to help us decide whether we were in the 3-5 categories? 3 or 5 categories, I should say. 3, 5, or 6. All 3 of those, we actually had hints given to us that would help us identify whether we were in those categories. And yes, while we can say it's the number of columns across, there's another hint that we could use. How do you know how many valence electrons there are? What's that? Based off the number of columns across? So you mean you're saying the same thing as she said? Which is fair, I get it. There's another hint. Periodic table gives it to you. What's the Roman numeral on top of the column in which gallium is located?
Number 3.
3. That is a 3 Roman numeral. What's the group number for, I already forgot it, selenium? 6. Group number for carbon? 4. Literally the Roman numerals are your valence electrons. You don't have to count across the period. Just look at the column name. That's the beauty of the periodic table, is it organizes this for you. And we've decided that we didn't want to deal with counting. Remember, chemists are lazy, probably lazier than you. Right? Which means we want that information stashed as quickly and accessible as possible. Right? So if we look for gallium arsenide, we just need to find the column that gallium is in, man. And that's column 3. We look for arsenic, that's column 5. And we have a 3-5 material. What column is cadmium in? And this is where, oh, we're getting 10 electrons. True. Look at the title for that column. It's 2. So if we're looking at the cadmium sulfide, it's a 2,6 material. Does that match 3,5? Some people are saying yes, right? And for those people that are maybe wondering how people would say yes, right? What we should consider is what happens when we swap out our system. If we're looking at a 2 material, what happens? 1, 2. If we look at the 6 material, what happens? 1, 2, 3, 4, 5, 6. What can we do? Promote 1 across. What do you end up with? You've got the 3-5 mimic. So 2,6 equally works as a semiconductor because it does align to silicon. You know, so well, how can you just promote that electron across? Remember, this is a bulk material. Those materials interact with each other in a way that your electrons can disperse. Okay? And they will disperse among the lowest energy systems. It will be lower energy to promote that electron across than it will be to keep it isolated to that individual element.
And we were given 2 options between 2,6 and 3,5, or 3,5 or
So which one is a semiconductor? They both are. So if you were given the choice between both of them, you would identify both of them because they both are semiconductors. Okay. Could we come up with other patterns? Potentially, but these are the 2 most common patterns that you see when we talk about semiconductors. Kind of, sort of? Okay. LED light work. We talked about the band. We did talk about that one in this class, right? We saw. Okay. And then dealing with our diode. So you're putting load on your battery where your electrons come out and will come in to your N-type conductor. So you're pushing electrons in, causing the electrons to then shuttle to the P-type. Okay, P-type means there's less electrons there, so there's a natural tendency for the electrons to want to flow there. You just have to give them a push. That's the point of the battery. When the electrons jump to the other side, you're now at a higher energy state. They want to relax back down to the ground state. Right? as they relax back down, that's now an emission of light. That's the whole point of seeing our battery, or not our battery, of our LED. Right? You have to align it in this fashion because you can't force it the other direction. Why not? For the record, I honestly don't really know because this is all new to me as well. Why can't we flip it and push the electrons the other direction?
Want to go like fill the empty space. Keep it right.
So fill an empty space. If we're looking at N-type, we're still looking at electrons in that higher energy state. Right? Even this, I think, is a bit questionable. Right? But if we pushed it the other way, what I would argue is happening is you now increase kind of that distance. You made it harder for your electrons to jump. Right? And if your electrons are harder to jump, that's going to be more energy that you have to force in. The next part is that where are they going to move? This, I think, is what you might be referencing. Is they need to move to an empty space. To go from the P-type to the N-type, what's in the N-type? Electrons. There's no space for them to move to. There's already electrons there. And if there's electrons there, it can't relax back down. And you're now stuck in the system where you can't actually get the electrons to move across. Kind of, sort of? Okay. So LEDs are more efficient. I don't think we talked about this. A little bit. Okay, so we're looking at our solar cells. Same general idea. You're taking N-types and P-types and you're layering them in a way that allows for your light energy to eject electrons to higher energy states so that you can get your load. Where does silicon come from? You're processing it. Where all our energy comes from. I feel really bad just kind of glossing through all this, but I'm pretty sure I won't say that for the recording. Plants use energy for sunlight, so we could go through and we could mimic what plants are going through and doing. So we could study plants to see how they transfer that energy along the different electron transport chains and how they're transferring that energy through to get it into systems that they could navigate. Because each of those are electron transfers, what could we end up doing with it? We could go through and quantify and practice. Sounds kind of exciting, right? Yeah, cool. So write the balanced overall redox reaction for this process. Determine what was oxidized and what was reduced, and what are your oxidizing and reducing agents. So start putting that information together. Okay, so what's going on? If we're looking for a balanced overall redox reaction, okay, this becomes one of those questions where we have to be careful and make sure that we answer the question that's asked. Okay? We're looking at the redox reaction for this process. What is this process? Chlorophyll is gaining electrons. That's coming from this statement up here. Okay, so if we look at our reaction involving chlorophyll, where does it gain electrons? Well, the electrons are on the reactant side. That's exactly what they need to be. So I could write that expression exactly as is. I don't know why I put an S there. I guess because electrons are plural. Okay. So what happened to that equation? What chemical reaction happened? Okay, that was a gain of electrons. The gain of electrons is reduction or reduced. I'm fine with either of those. Okay, what does that mean the chlorophyll plus acted as? This was our oxidizing agent. Okay, and if it gained electrons, what must the other one do? That must be a loss of electrons, which means it's going to have to be oxidation, which means it has to be the reducing agent. So if we look at that equation, the electrons are on the reactant side, which means it would be gaining electrons. I want it to lose electrons, which means I have to flip that equation. And of course, I didn't give myself enough space. 4H plus 4 electrons. 2H2O. Then go through and say, oh, well, to get the overall reaction, all we got to do is add it up. Depending on how you want to look at it, yes or no. I would argue no. When you add them up, we have to ensure that the electrons cancel out. Okay? So depending on your perspective on where you see the canceling process occurring, do you see it now or do you see it after you've added the two equations together? Okay? If you see it after the two equations have added together, that does become more work on your end. Ideally, what we would do is be able to look at the electrons being on opposite sides of the arrow, which is a good sign for them to be able to cancel, but they must be the same on both sides. Since they're not the same, what do I have to do? I have to run this first equation 4 times. Now the electrons would cancel. They'd be equal on both sides. What am I multiplying the bottom equation by? Nothing times 2 is what? Nothing. Okay, what are you multiplying the bottom equation by? 1. Okay, so you're still multiplying everything through. Okay, because there is some confusion on that. You're always multiplying by something. Okay, but that something could easily just be 1. Now we could go through and add our two equations together. We get 4 chlorophyll plus our 2H2O. 4 chlorophyll plus our oxygen plus 4H plus. And we now have our overall equation. Does that make sense? Everybody track that? If we talked about what was oxidized and what was reduced, okay, did we have to write out the equation? Okay. We could entirely skip the balanced overall reaction. What is oxidized and what is reduced? How could you answer that?
Whatever changed the amount of electrons on it. So the way that the
Okay.
first chlorophyll has a
Said another way. How do you answer the question, what is oxidized and what is reduced? The very first line, chlorophyll gains electrons. If chlorophyll is gaining electrons, what happened? It was reduced. Okay? The statement actually gives it to us. Okay? So you don't have to dig into the chemical equations. You can start to manipulate those systems directly as is. Make sense? With the extra information of the equations, you're absolutely right. You can manipulate those and help see those, but you didn't have to leverage that to do it. The question statement itself actually gives you that information. It's just coded. Chlorophyll is going to gain electrons. What does that mean? It had to be reduced. If it was reduced, what does that mean water has to be? It has to be oxidized. That's why we tie them together as redox reactions. Kind of make sense? Okay. Questions? So we can add to it because all we technically did was just look at the overall equations. Now we could go through and we could talk about what are the individual cell potentials. So here we've got the overall equation written for us, and we now have the cell potentials. Within those cell potentials, we could calculate our overall cell potential, our delta G, and our equilibrium constant for the reaction. We can then answer the question, is it spontaneous? So this is a whole slew of questions that are getting thrown at you. Right? Particularly when it comes to the quiz based off of past quizzes. Just because there's a part A does not mean there was only one question in that part A. Make sure you answer all of the questions. Okay? So if you're one of those people that's been missing points for particularly not answering the question, is this spontaneous? A highlighter may not be a bad idea to bring in for quiz 4 and for the final. So you can highlight each of the pieces of the question as you navigate them to ensure that you've actually answered every part of that question. Make sense? Okay, so also within this, we've got units to contend with and formulas. Okay, so blue box, spend some time to try and go through and process this, see what you come up with. If you got questions, raise your hand, and I will do my best to help you out. Okay, let's go through and talk about this. If we're going to figure out E-cell, so there's a couple ways to deal with cell potentials. First and foremost, a lot of people like to rely on this cathode minus anode thing. Okay, we've talked about it before. I don't like it. I personally don't like it because I struggle to memorize which one I'm supposed to subtract. Okay, that's really all it comes down to. You have formulas, so maybe the formulas help you. Okay? Even within that, it's not just here's a formula, I now have to apply it. Which one's the cathode? See, that silence is a problem. Okay? Because if you're not reflexing, oh, the cathode's this one, that formula isn't useful because you're going to have to do a bunch of processing anyway. Does that make sense? Okay. So for me personally, the way that I would go through and work on this is look at my overall equation and decide what do I need to do with my reduction cell potentials. So the chlorophyll plus shows up as a reactant in the reduction cell potentials. It shows up as a reactant in my overall equation. So I'm not going to touch that cell potential. That one's fine. Okay. However, when I look at the next equation, the O2 is a product in my final equation, which means what am I going to need to do that equation? I'm going to need to flip that. Can I squeeze that in? Maybe I can squeeze that in. I also like to go through and align the arrows, which sometimes instructors do, sometimes they don't. So my 2 H2O is my reactant, plus my O2, plus 4H+, plus my 4 electrons. Okay? What happens to my E cell potential? Well, I flipped the equation, so I need to reverse the sign. So it'll be negative 0.82. Okay? Now I can effectively delete this middle equation because that's not relevant to me anymore. When I go through and add up my two equations, I would get my overall reaction. Okay? Same deal to get my cell potential. Now all I have to do, whoops, put it 0 in the wrong spot. I just add those two things together. There's no which one is plus, which one's minus, or which do I have to add or subtract by. I just add them up. What does this get me for a cell potential? 0.08 volts. Okay? That makes it easier for me. I don't have to memorize some special formula. I just have to align the equations. And I would argue since most of chemistry is equations, you should be trained in chemical equations. Chemical formulas you shouldn't be trained in really at all. Okay? Who should use a chemical formula? Or chemical formula. I 100% disagree. I don't think a single student should be using chemical formulas to solve things. There's a few cases where you're nailed into it and you don't have any choice. But for the most part, you should be avoiding chemical formulas as much as humanly possible. The only people that should be using chemical formulas are doing repeated measurements. So this is someone within the field studying cathodes and anodes for their job. They now need a formula. Why? Because they're trying to turn off their brain as much as possible on the mathematics so that they can think about something else. Right? They should be thinking about the process of what they're going through and doing. They should be ensuring that they don't accidentally stick their hand in a vat of acid. Right? So the brain needs to shift around to those different systems. And unfortunately, what I think happens is we build an over-reliance on the formulas. Okay? And why does that become a problem? You now only know how to use a formula. You don't know how to think about how to solve that. Well, why is that a big deal? Do you know what else uses formulas really well? Computers. And if your only skill is that you can use a formula, you just lost a job. As depressing as that sounds. Okay? So what you should be pushing towards is the hows and whys these things come together. You should be the one trying to discover what that formula is to make your life easier later on. Okay? That's the point of this processing. So we've got a cell potential. Cool. What do we do with that cell potential? Okay? Now we need to figure out how to convert that into delta G. Okay? Within that system, that's ultimately just a conversion process. Do you know the conversion units to go through and deal with that? Okay? Is that something worth trying to know all the conversion units for? Probably not. So what do you need instead? This is where you've got a formula. Okay? So use formulas where necessary. Don't use formulas when all it does is muddy the water further. What is our formula?
N times Faraday's constant.
Delta G is equal to NFE. N was the number of electrons transferred. How many electrons were transferred? Well, that's interesting. Did I delete that? No, I didn't. That was dropped off. 4. We had 4 electrons transferred, which when we deal with trying to balance it out, which is what we did on the previous page, we should see that. So we get N times 4. 4 what? Moles of donuts? Moles of electrons. Okay, times Faraday's constant. What's Faraday's constant?
96485.
Coulombs per moles of electrons. Okay, why does this become important to highlight and ensure that you've got?
Go cancel out.
The units cancel out, which becomes important. And then also, what is typically asked of you in all of your quizzes? Show your units. So get used to that process of showing those units. And then we have to drop in our cell potential. Our cell potential was positive 0.08 volts. Excuse me. And a Coulomb volt is equal to
Joules over volts. Voltage is joules over coulombs.
what is a Coulomb volt?
1 joule.
That equals to joules. Which means when you go through and do this math, you get negative 30,000.
875.2.
0.2 joules. Do you want to write it as kilojoules? Maybe? What's that? If the question doesn't ask, don't do more work. Why not? You screw it up. Okay? Don't provide an opportunity for someone to take off points. Okay? If the question doesn't ask for it, leave it where it's at. Does that make sense?
Coulombs per volts. Or would you rather do joules?
I would rather see it as joules, and I think that's going to be an important statement because you're looking at delta G. You should write that out as joules. How do you solve for the rate constant? Now that I've written so much that I have no space to write it. Say again?
Like delta G equals T.
I believe it's RT.
Natural log K.
Whoops. So I draw an H. Natural log of K.
I was thinking it was a word for temperature. I'm pretty sure.
Oops. Why does it need to be negative? Because K should be positive, so whenever delta G is negative, you'd be able to go through and get a positive K. All right? So now what do? You could just plug everything in, or what you could try and do is actually solve for K first. I would argue you should solve for K first, and you'll get K equals e to the negative delta G over RT. I think I did that algebra right. And now I could plug in all the numbers that I've got. What's R? Why 8.314 and not 0.082115? They're officially both the exact same thing. So why do I pick 8 and not 0.08? It's the units that are associated with them. Yep, always the units. Okay, so we could go through and say E was our negative, and in this case it probably made sense to keep it as joules because R was going to be as joules anyway. 30, rounding that out at 800 joules is probably fine. Divided by our 8.3145, and of course this is going to be super tiny. Joules per mole times Kelvin times our Kelvin. Did it give us temperature? It did. 298 Kelvin, which I promise that's what it says in that corner. And then you should be able to get your answer. Damn.
Big number.
Okay.
258,000. You do not bet that.
I'm just gonna stick with 258,000. Assuming we get a second on that, we get 258,000. Yeah. And that becomes our equilibrium constant. What does that equilibrium constant mean? Seems a little suspiciously high to me, but I haven't done the math, so. What does that equilibrium constant mean? Awesome, it means products favored. And if products are favored, what does that mean? It's a spontaneous reaction. Could we have answered that without going all the way to K? Yeah, delta G being negative is a good symbol for us being a spontaneous reaction. The cell potential being positive is a good reason for it to be a spontaneous reaction. Make sense? So you're trying to tie all of that information together throughout the entire semester. Questions about it? Some questions?
You're missing units.
Units for the equilibrium constant.
What are the units on the equilibrium constant?
A little bit orange.
So we did have a we did have a conversation about the units for the equilibrium constant briefly. Right? We've ignored units on the equilibrium constant altogether. Right? Rate constant was a different deal. We needed units on that equilibrium constant. We dropped off and we just kind of ignored them altogether, which is suspicious, and it makes it more challenging for students because we complain about units, and then we don't talk about units at all for the equilibrium constant. Do you all remember why? It's a hard concept. It's okay. When we talk about our equilibrium constant, what we're doing is actually making a first approximation. Concentration is the closest approximation to what the equilibrium constant is, but it is not actually true. When we're talking about the equilibrium constant, the symbols or the things that go into it are the activities of each of the individual materials. Those activities are tied to concentration and their ultimate reactivity. So if we look at something that is more negative than something else, the more negative has a higher activity. That activity factors into your equilibrium constant because it's determining how fast that can, or not how fast, but determining our ratio of reactants and products. Okay? If you have to take a higher order chemistry class, maybe engineering class, you'll see it shift to activities. Okay? But I doubt anybody in here is going to have to deal with that. Maybe? Chemie? Are there any chemie people? No chemie. And then chemists, people that actually want to become a chemist. Yeah, I doubt anybody's actually going to see activities.
Did I plug it in wrong? Is I'm getting a different number? I don't know. Thank you.
Good observation. So that 30,000 from our previous calculation was negative. We've got a double negative. I've kept saying it throughout the semester. The minus sign will haunt you just like it's haunted me. Watch out for it. We good? Come on, work with me. Why aren't you? So how will the cell potential change if the oxygen concentration is lower? So there's a tougher question. It might be nice if we had more information in here, but how would the cell potential change if your oxygen concentration is lower? What is the oxygen concentration going to affect? This would be if we evaluated our tail end of this. So, well, actually, it's actually two new questions. I just looked at the bottom and I didn't realize the top. This first question is calculate your cell potential when the pH is 7 and the O2 is 0.0094 molar, okay, at 298 Kelvin. That's a concentration. That's two concentrations. How do concentrations factor into cell potential? They change the Q. That what you're talking about is the Nernst equation. So if we're seeing concentrations appear, we need to be thinking about the Nernst equation. So concentrations should mean our Nernst equation, which means our cell potential will be equal to our standard cell potential. Help me out, minus?
Yeah. R over two?
I thought it was RT over NF.
Yeah, that's not good, sorry.
It's cool. I'm the one asking you for help, so I appreciate anything you can give me. RT over ln of Q. So we could now look at Q. All right, what is Q? Q, and I don't know what symbol to put here because it's not really proportional, it's not really equal to, but it's solved the same way as K. And what was K? Products over reactants. So if we're seeing concentrations, we should be thinking K. And so if we wanted to deal with this and thinking about this as K, number one, it's not going to be K. Because if it is K, what happens to your cell potential? It's zero. Okay, it'll entirely cancel out. The net flow of electrons cancels, and we get nothing. There's no cell potential. All right, which does become an important statement. I don't know that you'd see a question on that, but that's why the Nernst equation actually works. Okay, where that's ultimately coming from. Right? So we could go through, recognize this, start to plug things in. The other thing that we could go through and do is effectively reverse the whole frickin' process we just did. You could go through and solve for what Q was from our previous question. Once we knew Q, we could backtrack to what delta G was. So we could say Q was products, we could go to delta G, and then we could go from delta G to our cell potential. I don't know why I'm drawing a delta on that. Right? That stepwise process all the way back is conveniently summarized for us in the Nernst equation. That's what it's doing for us. Okay? So, start it off, figure out what you've got to figure out to put together your Q, and then we can start talking about what's going to happen to your cell potential if your concentration is lower. Okay, so this one's going to rely heavily on how you calculate K. How do we calculate K? What are our products?
O2.
I see chlorophyll solid.
You don't count solids.
Why do I not count solids?
I don't know.
At least we're honest. Okay, when we're talking about our equilibrium expressions, the concentrations changing is what's important. Solid concentrations aren't going to change. As long as they're there, their concentration is constant. Same for our liquids. So we don't worry about our liquids, we don't worry about our solids. Does that sound familiar? That should sound kind of like what we said in Unit 2 when we first talked about equilibriums. You mean you got to pull that information back? Yep, you do. Okay, which you're going to have to pull some more information back in just a second. So cool, concentration of oxygen, I accept. Okay, as a product. What else? Cool, H positive. Is there anything else?
That's what I do.
So nothing in the reactants because those are all solids and liquids. But when we're dealing with our equilibrium constant, we do have to realize the coefficient does show up in our expression. That needs to come into the power of 4. Okay. It's a simple mismatch, but a simple mismatch that'll cause a cascade through that whole problem. Without actually trying to assign points all the way through for what that would translate into, I honestly don't know how many points that would cost you. Okay? Yeah, I honestly just don't know. Okay? So once you've got that, the rest of it should be pretty much just plug and chug. Your oxygen concentration, we don't have to manipulate too much, so 0.0094. And the H plus concentration is 10 to the negative 7 because we remember that our pH is tied to our H plus concentration. We have to hold that to the power of 4. We can now plug everything back into the expression. The next kind of place where we might get some kind of hang-ups, okay, you might get a small hang-up on R. What's our R? That needs to be the 8.314. Joules per mole times Kelvin. Okay, your temperature should be 298, and in the last place you might get a hang up would actually be N. N is the number of electrons transferred. That's 4 electrons.
Yeah.
Okay. How do we find 4 electrons from this equation?
You really can't.
You probably don't. You'd have to split that into the half reactions to piece those out. Okay, kind of makes sense? How are we feeling?
Also, the balance is wrong.
Sorry, the what?
The balance on the overall equation is wrong. 36.
Oh, yeah, because it's leaving off that 4 again. That's weird. Just for the sake of numbers, what do you get for the E cell?
0.523.
0.523. Oh, you got 2.4?
Yeah, you round.
Sig figs, I don't care. Okay. 0.523 or 0.524 is okay, volts. Which then, what do we do with the bottom one? How will the cell potential change if the oxygen is lower?
Oh, you got the one.
How could we figure that out? What's your approach? So I already know yours. Let's see. What do you have?
Put a smaller concentration.
Okay, cool. So a lot of people are just saying, you know what? Let's just change it. Let's just put in a smaller concentration. If you've already got it built into your graphing calculator or Desmos, all you gotta do is change that number and then see how it manifests. That is one way to go through and do it. What else could you do?
Using the natural log, like the smaller the number inside of it will give you small decimal value.
So if you know more about natural logs, you can plug in the number in your head to see how it changes, which is pretty much the same thing. What else could you go through and do? Okay, as a hint, none of that matters. Second hint, we're saying the oxygen concentration goes down.
Forward reaction is going to become more favorable.
The forward reaction becomes favored because we've decreased one of the product concentrations. Because we're forward reaction, what does that mean happens to the cell potential? Cell potential has to go up. So you can go back and use Le Chatelier's principle. You don't have to mess with any of those calculations again, potentially screwing up and misentering something. You can just use Le Chatelier's principle. We've put a stress on the system by dropping the concentration of oxygen. It's going to counter that by producing more of that oxygen. So we're going to see an increase in the cell potential to account for that. Kind of make sense? Questions? Okay, where are we at? Well, 45 is where we end, right? I'm totally going to regret asking this. Do you produces rust? What is oxidized? What is reduced in the reaction? What are the oxidizing and reducing agents? How many electrons are transferred in this reaction? How do we go through and process? What do you go through and see? Should we set this up the way I see it? F, that's a dangerous statement. Okay. I'll point out how I would go through and see this one. I think this one's a relatively short one, so we'll just tackle this on my end. Fe is going to have a 0 oxidation state. Okay. In the elemental state, when I go over and look at the products, there's a couple things I see. Okay. First, I'll go longhand. I would have 2 times X plus 3 times, since I know oxygen will always be a -2 in a compound, has to equal the overall charge of 0. 2x minus 6 equals 0. I get x equals plus 3, not 4. Damn it. Plus 3. As I go from a 0 to a plus 3, what happened? I became more positive, so that has to be a loss of electrons. Loss of electrons is oxidation. I don't know why I wanted to put a Z in there. If I did oxidation, that means that was the reducing agent. As soon as I've identified that, that means the oxygen over here had to have gained electrons, which means it was reduced, which means it was the oxidizing agent. Okay, now what did the question ask? What is oxidized and what is reduced? I've already got that answered. Okay, what are the oxidizing and reducing agents? I already have that answered. Okay, now I've got how many electrons are transferred. Okay, I didn't actually leverage that, okay, or set that up in full detail here. Okay, so I would have to double back, probably erase some of, well, I would have to erase some of this work so I could get through to some of those pieces. So let's clear that out. Going from a 0 to a +3, what did I do? Whoops. I had to lose 3 electrons. For the oxygen, starting at 0, going to a -2, that means it gained 2 electrons. So if I'm now looking at how many electrons are transferred, well, the 2 and 3 have to balance out. What's the lowest common multiple between 2 and 3? 6, which means 6 electrons were transferred. Kind of, sort of? I've now addressed all of those pieces of that question with minimal aspects behind that. We good? Last thing that I would potentially leverage for this question, and it looked like you might have a question. Give me a second. Okay. Particularly if I was just trying to be real fast in this approach. What happened to the iron?
Is it rusty?
Jerk. You gained bonds to oxygen. Okay, if it gained bonds to oxygens, what does that mean had to happen to it?
Oxidized.
It had to be oxidized. Okay, so I can actually look at just the formula changes to try and predict what happened through that system. Okay, I don't have to evaluate all the oxidation states. Do you guys remember all the oxidation stuff? That was the very beginning of this unit. You're going to have to use that material at least at some point. Questions about any of that? Yes, sir.
So why did we start out at 0
Why did we start out for 0 for what?
for the iron and the oxygen?
I don't know why I said for what. That was a stupid question on my part. I apologize. So where I would go with both of those is I always have to solve for the oxidation state. Okay? So iron, whoops, come on, pen, is just here. I don't need to worry about that 4 because whatever the oxidation state is on one of the irons is going to replicate for all the other 4. Okay? So I would say there's 1 iron times its oxidation state, and that has to equal the overall charge. The overall charge for that iron is specified in the upper right-hand corner. What's in the upper right-hand corner? Nothing, which then means X has to equal 0. Same process is going to play out for our oxygen. There's 2 oxygens, though, in that formula, times X, which is now going to equal upper right-hand corner 0. What's the oxidation state need to be?
0.
Has to come in to be 0. Okay, so that longhand form of the work is something I've internalized for anything in its elemental state. Officially, if you look at the rule sets that you were giving much earlier, it said anything in its elemental state is 0. You don't have to solve for it. It's just going to come down to where your comfort is. Why does the oxidation state change when we go to the product? Because isn't it still 0? It is, but there's now multiple elements contributing to it, and that's why our oxidation state is going to have to change. The one thing we will have to know is oxygen is going to come in at a -2. When? I'll accept 2 answers. One's more correct than the other. When is oxygen a -2?
What is it that equals to 1? Or like anything else?
Actually, that's a pretty good answer. Anything to the when oxygen is bonded to anything to the left, okay, or technically even below it,
Yeah.
okay, it's going to be a -2. If it's bonded to itself,
0
we got to be careful with that. It's not necessarily always 0, and I can show you a counterexample here if you really care. Okay, but it's going to change when it's bonded to itself, and it will also change when it's bonded to fluorine. Okay? Just because you kind of opened the question on that. What's the oxidation state for the oxygen in peroxide?
It's not bonded to itself though. That's hydrogen.
Really? Oxygen's not bonded to oxygen.
And with what else?
Oh, okay. So you'd have to evaluate all of the bonds connected to it. Okay? Oxygen in peroxide is actually a -1. Right? How would we go through and determine that formally? As a hint, it kind of helped to show the lone pairs, the non-bonding electrons.
I think it's like its own electrons and then minus. whatever.
Valence electrons minus owned electrons. Valence electrons for oxygen is 6.
Yeah.
Yep. Minus owned electrons.
Okay.
Well, it's going to own the lone pairs. It's going to own that bond. That bond represents
Two.
2 electrons. What about the next bond in between? They're sharing that evenly. It only owns 1 of those electrons, which means how many electrons does it own? 7, which means 6 minus 7, negative 1. Make sense? Questions? In the spontaneous reaction between iron and nickel, which element is oxidized and which is reduced? Write the overall balance reaction and calculate cell potential in delta G. So, you don't need to have speed necessarily, but speed can help. If we're looking at this reaction, it says spontaneous. Because it says spontaneous, what do you know the cell potential is? It must be positive. And it does ask for delta G. What does delta G need to be? Negative. That information just noted to the side can be useful because when you go through and do all the mathematical work, does your mathematical work check out? If it doesn't check out, you did something wrong. Okay? How do we ensure that we get a spontaneous reaction for our cell potential? One of your classmates provided this cheat to me. Take whichever cell potential is the most negative, flip that one. So if we go through, we have 0.036 or 0.23. The 0.23 is the most negative, so I want to flip that equation. Personally, for me, I would rewrite everything. That does not mean you have to, but you do need to ensure that you have the proper work. Okay, which means I need to flip the next equation. Nickel plus 2 electrons. That cell potential was negative. Note that every time I'm writing it, I'm including whatever it was written as, acknowledging then that I flipped it. So I'm going to go through and change that sign. Make sense? Now to figure out the overall cell potential, what do? Now all I got to do is add those up. I don't have to know cathode or anode. Okay? In this particular question, it's not asking which one's the cathode or anode. So me spending the time to find that information to solve this takes that much time out of the direction of what I need to go through and solve. So this cell potential should be, did anybody do the math that fast? Of course not. 0.19. Positive 0.194 is our cell potential. We've got, I didn't write the overall balanced equation. If we tried to go through and do the overall balanced equation, do we note an issue? Difference in electrons. How do we ensure our electrons match? The lowest common multiple between 3 and 2 is 6, so I can multiply the top equation by 2, the bottom equation by 3. I would get 2 Fe plus 3 nickel goes to 2 Fe. Whoops, definitely ran. Oh no, I didn't run out of space. Look at that. Plus 3 nickel. Cell potentials, I don't have to worry about doing any of the multiples on. I wish I had a better answer for why. Unfortunately, I do not. We just don't do it. Okay? That gets us our cell potential. It's coming out to be positive. We've got an internal check behind that. We can go through and deal with our oxidized and reduced. Leo, of course, GERS. So Leo, loss of electrons, was oxidation. I'm going to look for the equation that has electrons on the product side. Look at that. I even color-coded it nicely. This one was oxidized. This one was reduced. Calculate my cell potential I already have. To get the delta G, what do I need to do? negative NFE. Again, the tricky part is that N, we have to ensure that N is appropriate. When we balance the equation, we had to make sure we had the proper number of electrons to cancel out, which is 6, which means that's our N. At this point, we just plug and chug to solve our way through.
I just have a question roughly on, like a few slides back, but I can ask you later.
Okay. With that, we are officially done. Okay. Hooray, yay. Quiz on Wednesday. Yeah, and then I'll be heading to office hours shortly.